Okay, let me say a couple of words about the next homework. The first one, this is kind of, I think, helping with the idea of Galois theory and what we're going to be talking about these closed fields and so forth. Number one, consider the field extension Q inside QX. And here X is what you think it is. It's just a polynomial variable. So the field Q is Q, and then you have rational functions in one variable. Show that QX squared, which is an intermediate field, is closed, but QX cubed is not closed. And when I say closed, remember what it needs to be closed. The field is closed if you double prime it, you get the same thing. So when you double prime QX squared, you should get QX squared. But if you double prime QX cubed, you know. Number two, suppose that K inside F is an extension of fields, such that the degree of the extension is 2, right? So the quadratic extensions are especially sexy, at least in most cases. By the way, everybody here, now be careful with your answers being recorded. You all remember the quadratic formula, right? Yeah. Right. So what do you have to divide by in the quadratic formula? 2a. And if we assume that our polynomial is mine, right, we just have to divide by 2. So really the quadratic formula, if you look back in the old days and think about how did you derive the quadratic formula, you completed the square, blah, 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 and at the end of the day, you had to divide by 2. That process will work for any field unless the characteristic is 2. Right? So you can use the quadratic formula over any field that you want as long as its characteristic is not 2. And so that has some consequences here. Show that if the characteristic, so the field extension is of degree 2, show that the characteristic of K is not 2, then F is automatically Galois. So if you have a degree 2 extension of any fields, as long as the characteristic is not 2, it's automatically Galois. That's kind of cool. Give an example of a field extension K inside F with the degree of the extension equal to 2, and the characteristic is 2, and F is not Galois. Let me give you a little hint here. Think about the quadratic equation. You should come to the conclusion that the field should be pretty big, actually. Number C, give an example of a field extension such that the degree of F is 2, the characteristic is 2, and F is Galois over K. The relevant example here will be a big field. They'll all be characteristic 2. This will be big and this will be small. Well, this has to be big. This can be small. Number 3, if E is Galois over K and F is Galois over E, is it true that F is Galois over K? So is Galois, is that transitive? Prove the statement or encounter it. Okay, any questions? All right. So all right. Any questions from last time? All right. Let's see here. You're always learning about teaching, so I went and watched some of my grad students teach, just so I could say something authoritative on them. And one of my grad students, I was like, gosh, she's so much better than I am about paying attention to what's going on Zoom. People got any questions. So now since I watched her, doing this all the time now. So we were talking about this business with the closed fields and all this sort of thing, and we're sort of warming up in our proof the fundamental theorem of Galois theory, recall that X is a field intermediate field extension to the extension there, or X is a subgroup of the Galois group. Okay. So X can denote either a field or a group. Then closed X is equal to X double prime. If you recall, in general, we have X is contained in X double prime. We'll say that it's closed if you get an equality here. Let me point out that well, so let me state it this way. The previous results show there is a one-to-one correspondence between closed subgroups of G and closed subgroups of F. Given by E, field goes to E prime, which is the Galois group of F over. So the previous results that we proved last time show that there's that what we have is basically we have the statement of the fundamental theorem of Galois theory under the assumption that things are closed. That is to say, we've got a one-to-one correspondence between closed subfields and closed closed subfields and closed subgroups of G. So the way we were going to proceed from here is we were going to show that if F is algebraic in Galois over K, then all intermediate fields are closed, and we will show that additionally, if F is finite dimensional, then all subgroups of the Galois are closed. So one of these I'll do carefully, and then I will let you do the other one mostly as an exercise anyway. So lemma 8 to 10. Let's suppose we have this chain of fields. If M is a finite extension of L, then remember, when I prime, these are now groups, and it reverses the inclusion. That is to say that M prime is now a subgroup of L prime. This is less than or equal to. So in particular, if the degree of F over K is finite, then the order of the Galois group Well, this is kind of a, and I like that kind of sort of in particular note as well. Because what this says is, if the degree of F over K is finite, then that means that the number of automorphisms of F that fix K is less than this degree, right? So that gives you an upper bound on the size of the Galois. So by the way, after this lemma will be the one that I'll probably leave in your hands mostly, will be sort of the reverse where you start with the groups and then you get the fields, right? And it's kind of symmetric. So what we're going to do is we're going to prove this by induction on N, which is the degree of M over L. And let me note that is so if right. The base case is any one is immediate, because if the degree of M over L is 1, because of this containment, that means that M and L are the same thing. And so in fact, you've got an equality here, right? Because M and L are the same. Right, so no worries there. What I'm going to do in this induction also is I'm going to simplify this problem. So I'm going to reduce this to a simpler case. We're going to assume at this point that let's assume that the result holds for all I less than N. And of course our result, so we assume it holds for all I less than N. We now prove that it holds for N to do our inductive step. So I want to do a reduction here. My strategy is, the first thing I'm going to do is I'm going to try to reduce this to a simpler case. And what I'm going to do here is I'm going to pick some U be an element of M that is not an L. Since the degree of the extension M over L is finite, in particular, M is algebraic, over L. So in particular, U being an element of M is algebraic. So U is algebraic over L with minimal polynomial f of x. And let's say we will assume that the degree of f is k, and of course k must be strictly bigger than 1 because we're assuming that u is not in L, so you can't have a linear polynomial then. So the degree of LU over L is K, and of course, because of the fact that degrees multiply, and the fact that the degree of M over L is N, then this must be K over N, which has to be an integer, of course. So if is less than N, and of course, if K is less than N, then that squeeze, then L prime over M prime is equal to L prime over LU prime, LU prime over M prime, which is less than or equal to So what we get is L prime over M prime is equal to this product, right? Because this is groups. This is the same property here. L intermediate group, M prime. That's N over K. That's K, which is N. So we only need to worry consider the case K is N. Well, I need to get us a certain case K equals N. And in this case, we have M is equal to L. So we make this reduction and we proceed to deal with this case. Deal with this case. What we're going to do is we're going to one-to-one map from the set of left cosets M prime and L. M prime and L prime. To the set of distinct roots of F and L. Which has notice that, of course, F has degree K, which we decided was N, right? And so if we can construct a one-to-one function from the set of left cosets of n prime and L prime into the distinct roots of f, right? Then that'll be a one-to-one function from however big this set is into a set that is no bigger than n. That would mean that this thing has to be less center equal to n, which is the degree. Everybody okay with the strategy there? So what we're trying to do is to construct a map and set of left cosets of n prime and L. The number here is precisely this. A one-to-one map from this set into the set of distinct roots of f, which has no more than there's no more than n of those because it's bounded by the degree. So how am I going to do this? Well, so let tau n prime be one of these cosets, and sigma in the Galois group of f over m. And remember, the Galois group of f over m is the automorphisms of f that fix m, and so it's n prime. Since U is an M, then well, what happens to tau sigma U? Well, U is an M, so sigma of U is equal to U, right? Because by definition, sigma fixes everything in M, which includes U. So this is tau of U. And so from this, I can glean a nice observation about how the elements of the coset act on this. So every element of the coset now m prime acts the same on U. Right? Because, right, so everything in the coset, first you apply the sigma in m prime and it doesn't do anything. So every element of the coset does the same thing that tau does. And this allows us, so this observation lets us define our map. We're going to define let me call it something. T, S, T. Via, I take tau n prime, and I go to tau u. Notice that, right, so my input is one of these cosets, my output is going to be tau of u, and notice that since f of x is L in X. Yes, it is. You know. So f of x is this polynomial. It's an Lx. So all my beautiful little L's are in L. Yes.
What are our elements? Are they functions?
Yes.
Okay, so tau is a function, and then tau of n prime is a constant.
Right. So tau is actually an element of L prime. So tau is actually a function on
Okay.
F,
So
and
that's
it
how
fixes L, and it fixes L.
Okay, that's how it's acting on that. So the elements of U were all of the elements and that it fixes.
Right. So tau lives in L prime. Right. What that means is tau fixes all the crap in L.
Yeah.
Right. So, and actually, that's important here because notice that f of u equals L in u n plus L1 u plus L0. And we said that u is root of this, right? So when you apply tau to this, because notice that tau, because it's an L prime, fixes everything in L. So I mean, so basically the L's pass through tau like neutrinos here, right? Just, comes right out. This analogy. But anyway, so what we get here is tau of u is also a root because applying tau to 0, of course, gets you 0. And so this justifies my input is a coset, and my output is indeed a root of f of x, right? Because tau u is also a root. So this means this goes where I want it to go, right? So my input is tau in prime, that coset, my output is tau u, right? Tau u is again an element of t, which was I'm glad T is the set of distinct roots of F and L. So there you go. It's still a root. Okay. Notice that because also it goes where it needs to go. That is, the output is a root of F. So it goes where it needs to go. And the fact that this remark here shows that it's well defined, because it doesn't matter what representative that you pick from M prime, you get the same tau u. So it's a well defined function. We need to see that this map is 1-to-1. So suppose, and of course I need to do 1-to-1 the old fashioned way here because this is just a map, it's just a function here. Suppose that phi of tau in prime equals, I need to show that these two represent the same, that tau and tau not represent the same left coset. What does this mean? So tau u therefore is equal to tau naught u. So tau inverse, tau naught fixes u. And that is why our reduction pays off. Tau inverse, tau naught fixes m, which is LU. Because I already know that these guys fix L, all they have to do to fix M is to fix U as well, and there we go. So this is why the reduction pays off. Where we reduce to the simple case where M is a simple extension. And so that means that tau inverse tau naught is in prime because it fixes everything in M. Therefore, tau in prime, tau naught in prime. Because of this, they must represent the same coset. Therefore, hence, P from ST. So cardinality of S is less than or equal to cardinality of T. Cardinality of S is L prime M prime less than or equal to so that does it for us for this week. Okay, we're actually fairly close to finishing this up. Let me put the companion of this lemma up next time. Or let me put this up now, and you all should see if you can figure out how to do it. The ideas in proof of this are very similar to this one. Lemma 8 to 11. Like K and F be fields. And H inside J. So the Galois group of F over K. If the index of H and J is finite, then the degree of the extension is less than or equal to that index. Notice this is a companion. In the following sense here, in the previous lemma that we took a while to prove, if we had the extension of fields is finite degree extension, and the index is less than the degree. Here we have if the index is finite, then the degree of the extension is less than the index. Right. So notice that with both of these lemmas put together, we get exactly what we want. this lemma follows from these previous two. And this is the last one. So lemma 82. This kind of ties together what we have. .12. Now, the fields and H. So A. L is closed. And M, the degree of M over L is finite. Then M is closed. And we get 12. And also, if H is closed, we can start from the other point of view. And the index of H and J is finite, then J is closed. And H prime, J prime, J. In C, if F is finite dimensionally, Galois over K, then all intermediate fields and all subgroups of Galois group are closed. Then all intermediate fields and all subgroups Galois. And in this case, the degree of the extension is precisely equal to Galois group. All of this follows from the previous couple of lemmas and stuff that we did before that. But any questions? There's actually one more piece of fundamental theorem that, of course, let me also point out that with a lot of the applications, one of the things that we're going to talk about is I'm going to talk about some Galois fields with infinite, or I'm sorry, some Galois groups for infinite fields, but they can be very hard to compute. a lot of what we're going to do is in this case where the extension is finite, as a matter of fact. There's one more piece of fundamental theorem that we really haven't tackled yet, and this is the business about intermediate groups being normal and the corresponding field is Galois base field. So, definition. Let's start to deal with that. So I need a definition here. So let's sigma in Galois group. And E is an intermediate extension of extension K over F over K. It's said to be stable. Yeah. Sigma of E is contained in all sigma in the let me give you a non-example, so I think it might illustrate some things. I want to go back just with a piece of this table that we had before. This is not the complete lattice. Notice I'm missing one of the, I'm missing the real field, right? But let me point out that these two pieces right here, let me like incomplete picture. These are not stable. Because, for example, the homomorphism or the automorphism of complex conjugation swaps these two fields, right? So, for example, omega cube root of 2 under the automorphism of complex conjugation goes to here. They were stable. No, no. This actually goes to here, which is not it here, right? This is stable. Because every automorphism of this thing certainly fixes Q, and it doesn't fix omega, but it takes omega into the same field, right? So in other words, notice that, for example, what does complex conjugation do? This one, it takes omega to omega bar. But remember, omega bar is -1 minus omega, which is still in that field. So even though complex conjugation is not the identity, this much is satisfied. Sigma of E is still contained in A. So the field Q omega is actually stable, and the other two are not stable. They're completely tossed back and forth. Here's something else we can say. We can say that tau in the Galois group of E over K. And of course, I just mean the automorphisms B that actually fix K is extendable to F. So this is a natural thing to ask. So I've got an automorphism of E. When can I extend this to a E in a natural way to an automorphism of F? There's a sigma in the Galois group of F over K such that when you restrict sigma down to the subfield E, get tau. Let me note, it's probably worth recording here, but note the tau is extendable to sigma, then if you can extend tau to a sigma, then sigma of E is contained in E, just because by definition, what it means to be extendable, when you restrict sigma down to E, you get tau, which is not what this would be, so it's still inside there. Okay, any questions on that? Okay, so let me give you a lemma here that we're going to need. You're going to see some familiar bits come up with regard to our statement of the fundamental theorem of Galois theory. Lemma 8214. Suppose I have a tower of fields there. If E is stable, relative to the Galois group of F, then E prime, that is the Galois group of F over E, is actually a normal subgroup of Galois group of F over K. And B, if H is normal in the Galois group of K, then its prime is that H prime is actually a stable intermediate extension. Proof of this is not too bad, but I think that it's probably best that we get to that next time. Any questions? Well, once we get through the last bit of the proof of this, we're going to talk about, we're going to get kind of down and dirty. We're going to talk about separability and stuff. And then at the culmination of this is I'm going to actually show you how to compute some Galois groups. I'm going to show you some tricks, show you how to do something practically, solve global radicals, things like that. Some without proof. Any questions? Well, I would encourage you all to roll by the math club today. It's about convexity, which is, of course, convexity is kind of weird because that shows up in pretty abstract mathematics, but it's also like it's important in linear programming, right? I mean, it's important kind of all over the place. Should be a fun math club. Hope to see you all. Don't forget homework today. Let you need more time, let me know. Other than that, you guys have a good weekend. We'll see you on Monday.